So that's once you understand this table. Let's come back to this formula, to this thing. What should I say? This you should rewrite this algorithm into non-recursive format, and then do it in a bottom-up fashion. Okay, I mean this is really not a right way. Okay, to what should I say? To conduct like a dynamic programming. Okay, dynamic programming is not. I mean, because usually when you do a recursive code, you always start from a biggest, a most complicated problem, and then going it's like a top down, from top to the bottom. Okay, but dynamic programming is different. Okay, you cannot do it this way. Okay, you have to do it in a bottom up fashion. Okay, so I mean you should do it it should be you should have a double nested loop, like one for I, one for J, and then use this simple rule. Okay, first you need to fill out this boundary cases, and then use simple rules to construct this thing either color major or row major. Okay, so as for so now we know how to compute Cij, right? But remember, our problem is not to compute Cij. Cij, what is Cij? Or CMN? CMN represent the size of the longest common subsequence, right? But our problem is not for you to compute the size of the longest common subsequence. Our problem is for you to compute the longest common subsequence, right? So there's a difference here, right? So what do? I mean, once you have this table, how do you construct the longest common subsequence? Or put it another way, okay, there's a hint in this table, okay? You see every match, for example, there's a match, you come from a diagonal, right? For example, this B and that B, there's a match. It's the Ci minus 1, J minus 1, J plus 1, right? So it comes from a diagonal. There's a match, you come from diagonal, and so on, right? Right? So that slash indicate that number comes from, because of a match, it comes from diagonal one, right? So there's such a hint for this slash. Okay, so think about this. Okay, now you want to construct, recreate the LCS out of this table. How do we do it? You do it, okay, like this. Okay, say this is 4, right? If this 4 comes from left side or right side, left side or top, okay, let me find something. Well, for example, 3 comes from top, right? So you go up. Okay, you don't go this way, you go up. And then, for diagonal, now you understand there's a match. There's a match, so you keep, you keep B, you try to output that B. But you say, oh, how about in this case, like the left side and the top are the same? Then you have the option to go either way. Okay, so let me repeat. Okay, so this is, the construction is to do it like in the opposite, in a reverse manner. So for example, let's go left. Okay, oh, there's a diagonal. Then okay, we try to output this A, because this A is a match. So output A, go here. 3, oh, we know 3 comes from the left, because it's 2, 3. We get the max, the larger one of these two. So we go this way. And then there's a diagonal, right? So it's a B. So previously we output A, and now we output B. So here, 2 come from here. And we have another diagonal. So we output C. And once we are here, okay, 1 come from here, and we come from here. Okay, there's a match. So it's going to be, so we output, what do we output? We output A and B, and then what else? C, and then B. Okay. So of course it's the opposite. It's a reverse, right? So it should be like a B, C, B, A, right? B, C, B, A. That's just one of them. You have like a different way to generate like the longest common subsequence, because, for example, that's when we go left, right? So we can easily go up. If you go up, then there's a match B. Okay, we go here, and there's another match A. Okay, so we output B, output A, and then 2. Again, we can go either way. Okay, let's go up. Then we have D, and then another diagonal. So B, D, A, so B, A, D, B. So reverse is B, D, A, B. B, D, A, B, B, D, A, B. Okay? So you have like a lot of options. So each one like give you a longest common subsequence, but of course it will be outputted in reverse manner. Okay, just need to a easy approach is just to dump that output into a stack and then pop it out. Okay, because stack will automatically reverse the output for you, right? Okay, so something like that. So reconstruct LCS by tracing backward. Okay, and this BCBA is one of them, but it's not necessarily the only one. There are a lot of possible, longest common subsequence out there. Okay. So space is a theta MN. Okay, and you could. It is possible to only use this much space to do the job. Okay, I want you to think about that, how to get this done. Okay. A hint is like this. A hint is like this. Okay. When you construct this table, of course, like if there's a diagonal, you need to remember, right? Or you can output it, right? You can output it. You can just directly output it. But the issue is like this. Okay. When you construct, when you have this, remember I told you like it could be column major or row major. Let's assume that we do it column major. We have this one. When you have this one, okay, do you need this column anymore? You don't need this column anymore, right? I mean, what I meant is like once you have this column, then I mean, when you try to construct this column, you only need to know this column, right? This part is no longer useful, right? And when you create, say, when you are here, you are in the position to compute this column. You only need the content from this column, right? Right? So the previous columns no longer useful, right? So yeah, I mean, you need to remember like those diagonal positions. But in terms of the table, only two columns will be good enough, right? One column for memorization, the other column that, store like what you are doing right now, right? So that's the reason you only need a min mn. Why is a min? Because you could do row major, column major, you can do row major, right? Whichever is smaller, you do it that way. And you only need two of them, so it's like a 2m or 2n. Okay, just to give you a hint. Okay? So that's it for this chapter. Okay? So we finished like dynamic programming in about half a lecture. But I want to tell you that there are so many different dynamic programming problems out there. Okay? LCS is the most, what should I say, like the most classical one. Okay? There are also like, for example, like matrix multiplications, a lot of different type of like dynamic programming problems. So yes, I'm going to assign some other dynamic programming problem as homework. Okay, actually, like for example, like when I took my qualification exam, okay, for my PhD at Ohio State, the dynamic programming is the most, you could say it's a most difficult part to prepare because there are so many different variations out there. Yeah, but yeah, we are only going to, confine our discussion in like the classical ones. Okay, so that's it. So then that's the next topic is the greedy algorithm. Okay. Similar to dynamic programming, there are so many problems, classical problems for greedy algorithms. Okay. But we are going to use like the minimum spanning tree problem to motivate this algorithm design technique. Okay. Minimum spanning tree is also one of the famous graph algorithm. By the way, did who teach you data structure class? 张桂林老师吗 ？OK， 你们都是张老师的学生吗？他有教那个 graph algorithm，graph 那个 graph 那边部分吗？有教到哪边？方便问吗？还是忘光了？有教树嘛，对不对？应该是先 tree 嘛 ，and then graph，right？ graph I mean 有教到哪边？我先确认一下。忘了。还是只教了一些 graph 的一些譬如说 graph 的那个 data structure representation，譬如说那个adjacency matrix、adjacency list 那些东西，还是你们记得吗？还是全还给张老师？张老师会很伤心的。对啊，如果你们全忘光的话 ，OK， 不要到时候过了1年，人家问说，哎，你们演算法谁教的？孙老师教的，你们还记得什么东西吗？也全忘光了。对啊，那真的是不太好。好吧，你们没有给我 feedback， 所以我也很难那个。好吧，我就照我的准备来讲一下好了。就是这边对 graph 的一些比较像 graph representation 那些东西，我可能会讲快一些。So greedy algorithm, and also graph, So graph, this is a review, I know you data structure must have covered this part, but again, let me repeat. This is a review. So there are two types of graph. One is like a directed graph. One is undirected graph. Right? Directed graph G is represented as a VE. And V is a set of vertices, and E is like represent like edges. If it's directed graph for example, from vertex A, B to vertex B, the edge AB is different from the edge of the vertex BA. You know that. So in the undirected graph, I mean it's similar. We have G equal to VE, and edge and set E consists of unordered pair. This one is ordered pair. E is ordered pair, but this one is unordered pair. So in either case, we have like a size of E, is bounded by V square. It's because it's no matter it's ordered or unordered, it's E is each edge can be represented by two vertices, so it must be bounded by big O V squared. And also, if G is connected, then the size of E must be greater or equal to V size of V minus 1. This is if G is connected and the number of edges like a V size of V minus 1, then you are talking about a tree, right? I think this is data structure must have covered that. So that implies, the log E, number of edge, if you get a log, it must be, log V, because, well, E is bounded by V squared, and so at the most, you have V squared, number of edges. So if you get a log, I mean, it's 2 log V, right? And the E, if graph is connected, E, is at least this many. So obviously, you have upper bound, you have lower bound. So, so if the graph is connected, the log E is theta log V. So this is what you should have known. And again, what you should have known, adjacency matrix, of a graph, is represented by a matrix, n times n matrix, if you have n vertices, So Aij equal to 1 if ij is in E, 0 if ij is not in E, So adjacency matrix, can be used to represent a graph, either directed or undirected, And this is an example. This is directed graph, by the way. So you can see that. in this matrix, okay, we have 1, 2, 3, 4, 4 edges. So in this matrix, only 4 elements are 1. All the other elements are 0. Okay, so if so we have like so this is n by n. So obviously, like you know, the size of I mean this data structure is theta v squared. Okay, this storage. Okay, if you have like a lot of like edges, okay, in other words, if your graph is dense, then it is a good data structure to represent dense graph. By the way, if you ask me what the dense graph represent, the dense graph means that the number of edges is, you know, is theta v squared. Okay, so if you have a lot of edges, what do we mean by a lot of edges? So it's like in the order of v squared. Okay, in that case, then we prefer to use adjacency matrix. Okay, so for adjacency list, okay, it's like you know, for each node, okay, we represent like what it connects to. For example, 1, okay, we have a link to 2, we have link to 3, so 2, 3. 2, we have a link to 3, and so on. So adjacency list, I mean, you know, is something like this. And for undirected graph, the size of adjacency of a list for a node is the degree of the node. For directed graph, the size of the list of a graph of a node is its out degree. Yeah, and also there's a very famous handshaking lemma. Okay, so if you add all the degree together, I mean all the degree, I mean the degree of all the nodes together, is going to be 2 times the size of the edges, because like you know each edge is counted twice. So this is one of the famous handshaking lemma. Okay, for undirected graph. Okay, and adjacency list use this many storage, this amount of storage, and it is preferred for sparse graph representation. Again, what is a sparse? What do we mean by sparse graph? It means like the number of edges is theta v. Okay, is if that's the case, then we prefer to use adjacency list, because like this way we save the storage you know, space. Okay, so a quick review of the graph material. Now we come to the motivate problem of this lecture. Okay, the minimum spanning tree. Okay, so what is the minimum spanning tree? Okay, so given a connected undirected graph, okay, and with weight function, so each edge is associated with a weight, okay? So you could assume, okay, for simplicity, okay, you could assume all edges, their weight are different, okay? In general, of course, we could, this assumption could be removed, okay? Some edge could have the same weight. But if some edges have the same weight, then the minimum spanning tree is not unique, not necessarily unique, okay? But if each edge has the different weight, the minimum spanning tree is unique. Okay, it's unique. There's only one such minimum spanning tree. Okay, so given this input, we want to output a spanning tree T. Okay, this tree, okay, will connect all the vertices in your G. Okay, with the minimum weight. So in other words, okay, it's going this tree, this minimum spanning tree is a subgraph. It's a subgraph of the graph G. Okay, first it will connect all the vertices. Second, it's going to use the minimum number of edges and the minimum number of total weights. Okay? I mean, when you connect like all the vertices together to form a tree, yeah, I mean, you must have the minimum number of edges. But the more important thing is minimum total weight. This is important. So for example, say this is a given graph. Okay? And yeah, we have 1, 2, 3, 4, 5, 6, 7, 8. 8 vertices. It's considered like a complicated example already. So it's a minimum spanning tree is represented by the red edges. And you can see that we have 8 vertices. So the number of edges will be 7. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. Yeah. So number of vertices is -1. And also, okay, the total weight, okay, in this example is a 6 plus 5, 11, 20, 27, and 42, and 50, 53. This total weight, 53, is the smallest among all the spanning tree. Okay, among all the possible spanning trees. You could give it a try, okay? Try to create any other spanning tree, and their total weight must be larger than this one, okay? And this is this minimum spanning tree is unique because each edge has different weight. Obviously, each edge has a different weight. If some edges have the same weight, yeah, you could end up with like a multiple minimum spanning tree, as I said earlier. Okay, but for now, let's assume they have different weights. Okay, all the edges have different weights. Okay. So, okay. So now, once you understand this question, how do we do this? How do we do it? Okay. Let's take 10 minutes break. When we come back, we will continue. I hope to finish. Well, I hope to finish most of this lecture. I'm not sure if I can finish the whole thing. Okay, but I think like it's not like I'm trying to catch up the progress, but you know, some lectures are shorter, some lectures are longer. So depending on the size of the material, I mean, I'm going to sometimes I'm going to cover like more than one lecture, but yeah, I mean, I hope, I mean, I want you to understand this is not like I'm trying to speed up. I'm not trying to speed up. I mean, I don't think if you have any question, okay, if you feel like I'm too fast, obviously you can let me know. But I do not think I'm speeding up. Okay, I'm just using the same pace. Okay, yeah, just want you guys to know like so. Next lecture, I hope I can finish this one and also cover. Oh yeah, and another thing is like the shortest path. There are 2 lectures on shortest path, single source shortest path and all-source shortest path. So I'm also planning to finish that one. And and min-max flow, and then NLP, the NP problem. So let's see what I can do. But if it's going to, I feel like it's too fast, I'm going to cut down the number of lectures, okay?